Finite Math, Chapter 10, Section 4. Last section of the semester, folks. We're going to start with an example. Now, not one you have to work, but just one to kind of illustrate where we're going with this. So suppose a bank is interested in improving its service to customers. The manager decides to begin by finding the amount of time tellers spend on each transaction, rounded to the nearest minute. The times for 75 different transactions are recorded, and the results are shown in the table, where the frequencies listed in the second column are divided by 75 to find the empirical probabilities. All right, so we have the time. Empirical, by the way, is observed. Since this data comes from observation and not from theory, it's called empirical. So there were 3 transactions that took 1 minute. So the chance of you having a transaction out of these 75, randomly picking one that lasted a minute, would be 0.04 and so forth. So you could see the data all lined up here. Now in this example, it's possible for the transaction times to take on any real number value greater than 0. The manager rounded them to the nearest minute, but in reality, 1 minute transaction could have been 1 minute and 15 seconds. Or a 5-minute transaction could have been 4 minutes and 50 seconds. So really any real number could have been used as long as the value was greater than 0. A distribution where the outcomes can take on any real number value within some interval is called a continuous distribution, and the graph of a continuous distribution is a curve. Now on the next slide, we're going to see a histogram and a frequency polygon that represents the data from this particular example. And you can see that the frequency polygon really does look like a curve. It's represented by a curve, and we don't have to have our data points at exactly 1 minute and 2 minutes and so on, because the times in between actually are real points that you could have. Data are normal or normally distributed when their graph is approximated by a bell-shaped curve. And we've kind of seen this before. Graphs like these are also called normal curves. The mean, or the average of the data on a normal curve, is symbolized by the Greek letter mu, and the Greek letter sigma is used to denote the standard deviation. Now there's really many normal distributions. They all depend on the values of mu and sigma. Next slide, you're going to see 3 possible curves. Okay, and really it depends on the value of sigma. It depends on how far spread apart the data is. If you have data that's clustered really tightly together, it's going to look like the distribution in the middle. If your data is spread out farther, it's going to look like the one on the right. The one on the left is kind of a middle ground. Now, every normal curve does have these properties. Its peak, the highest point, is directly above the mean. The curve is symmetric about the vertical line through the mean. In other words, the left and the right-hand side are mirror reflections of each other. The curve never touches the x-axis. It extends indefinitely in both directions. And the area under the curve and above the horizontal axis is 1. The reason it's 1 is because it represents the sum of all the probabilities of that particular distribution. And when you add all the probabilities up for any distribution, you always get 1. Now, normal distribution is determined by the mean and the standard deviation. As we just saw a minute ago, a small standard deviation produces a tall, narrow curve, and a large standard deviation means the data are very spread out, and it gives you a flat, wide curve. Since the area under a normal curve is 1, we can find parts of the area, and they can be used to determine the probabilities between data values on the horizontal axis. In other words, with our banking example, what if you wanted to know what's the probability that you pick a transaction that lasted between 3 and 5 minutes? Well, if you plotted the data on a normal curve, you could actually find the area under the curve between the points 3 and 5, and that would give you the probability of getting a transaction that would last between 3 and 5 minutes. So the area of the shaded region under the normal curve from A to B, as you see here, is the probability that an observed data value will be between A and B. Here's a couple of examples here. The one on the left has specific numbers put in. The one on the left, you're finding the probability that, I think this was a graph for rainfall, that the rainfall will be between 25 and 35 inches for the year or something like that. The one on the right is a little more generalized. You want to find the probability that something happens between value A and value B. You're going to find the area under the curve between A and B, that shaded region. The probability that an outcome will be between two values on the horizontal axis is equal to the area under the curve between those two values. That's just restating what we've just said. Now, to use normal curves, we need to be able to calculate the areas under portions of them. And since there's such a wide variety of possible values for the mean and standard deviation, the easiest way to do this is to standardize it. We're going to convert the curve into a standard normal curve. A standard normal curve has a mean of 0 and a standard deviation of 1. And to calculate the area under the curve, what you need to do with your data, with your raw data, is you need to find the corresponding values on a standard normal curve. These values are known as z-scores, and I'm going to show you how to calculate these in a minute. Now, the good news is that once you know the z-scores, you want to find the area between. You can use your calculator to do that. On your calculator, you're going to push the second button and then the VARS key, the V-A-R-S. This key is directly to the left of the clear button. This will bring up what's called the distribution menu. You'll notice in blue above the VARS, the variable key, it says DISTR for distribution. You're going to select normal CDF. This is number 2 in the menu. Number 1 is normal PDF. You don't want that. You want the second one, normal CDF. When you hit enter on the home screen, you're going to see this, normal CDF with an open parenthesis. What you're going to do is fill in the lower z-score, a comma, and this is what I'm talking about. You want to go to the distribution menu. You want to go to number 2, the normal CDF. It'll look like this when you pull it up. I put in 0 and 3, so this would give me the area between the mean and 3 standard deviations. So I get that that's 0.4986, so about 0.499. Now, some of you have a calculator that when you pull it up, it looks like this. And what this does is it will actually allow you to put in what you're interested in without converting it to a z-score. So you would actually put in the lower and upper numbers for the raw data you're interested in. You would give the mean and the standard deviation for your data, and then you click on paste, and that will paste it into the home screen. Then you hit enter, and it will give you the area under the curve for that data. So here's an example. I'm giving you the z-scores, and by the way, with that screenshot we just saw a minute ago for that last one, if you leave it, the default is a mean of 0 and a sigma of 1, a standard deviation of 1, which is the standard curve. And so you want to leave it at that if you have that on your calculator for these next few examples, because I am giving you the z-score, which assumes that you have a mean of 0 and a standard deviation of 1. So try these examples. I would do this in your calculator. You can do it using tables, but the calculator is a little more convenient. So practice using what I just showed you. Find these, pause the recording to do it, and then resume to check your answer. Okay. I did refer to a figure you didn't have there, but you really didn't need it. You just needed to put the numbers into your calculator, and you should have gotten 0.3413. Now, we're going to represent this as a percentage of the total area, which is 34.13%. So the probability that something would happen in this curve between 0 and 1 is 34.13%. Okay, now we're going to find the area between negative 2.343 and 0. Again, when you're using the regular method of doing this, you want to put in the lower score, comma, upper score. All right, pause the recording to try this and resume to check your answer. Okay, and again, they're referring to the table, and you can use the table if you want to in the back of the book, but the calculator is a lot more convenient. You're going to select normal CDF, and you're going to put in negative 2.43, comma 0. And that should give you 49.9 0.25, well, 0.4925, which is 49.25%. And you can see there, if you think of the mean as being in the half, at the halfway point, which it is, that's almost half of the curve that's been colored in there. Okay, let's try another example. And here they're giving you the z-scores again. So give this a try, pause the recording, give it a try, and resume to check your answer. Okay, you see here the sketch, and we're looking at a z of negative 0.88 and 2.35. They're illustrating those on the curve. Think of, again, if you think of your mean as 0 and think of it like being on a number line, anything to the left is going to be negative, anything to the right is going to be positive. Now, if you use your calculator, then it's going to go straight for the correct answer, which is 0.8012. And another way of doing that is to find the area from 0 to 2.35 and negative 0.88 to 0 and add those together, which is what they're talking about there. All right, again, these are the z-scores, 0.58 and 1.94. The z-score just simply tells you how many standard deviations your data point is above or below the mean. So pause the recording, give this one a try, and resume to check your answer. Okay, again, putting this into your normal CDF should be pretty easy. You're just going to select normal CDF. You're going to put in 0.58, then a comma, and then 1.94. And that's going to give you 0.2548 rounded, so 25.48%. Okay, this one's a little trickier. It says the area to the right of 2.09 standard deviations above the mean. This can be really helpful to draw yourself a normal curve here, kind of estimate where 2.09 is, and kind of give yourself a picture of it. Now, I'll give you a hint. What you want to do with your z-score, if you want to use the calculator, you're starting at 2.09, so that's going to be the first number. Now, it says to the right. In other words, you're not stopping. You're going to go out as far as you can go to the end of the curve. Well, the problem is technically this curve never ends. However, there comes a point when going further out just really doesn't change anything about your information, about your area. So what we do whenever we want to figure out something that goes from a point all the way out to the very end on the right is we use a big number like 99 to represent that end point, even though there's no end point. So what you're going to do in your calculator is you're going to do a normal CDF. You're going to put in 2.09, and then you're going to put comma, and you're going to put 99, and that should give you the correct answer. So why don't you pause the recording, give that a try, and then resume the recording to check your answer. Okay, hopefully on your calculator you got 0.0183, which would be 1.83%. Again, what we do on the calculator for this, because as you see in the picture, you're going from 2.09 basically on into infinity. Well, you can't put infinity in your calculator. But again, like I said, there comes a point where going higher just is not going to make a difference in the area. So what we tend to use for our right endpoint when it's supposed to go all the way out to the right is 99. By the same token, if it had said, what's the area under the curve to the left of 2.09? Again, to the left, it's not really giving you a starting point. However, and the curve doesn't have a starting point because it goes on forever. However, there is a point past which it really doesn't matter anymore. So usually we use a number like negative 99 to represent the very beginning of the curve. So if they wanted to know the area to the left of 2.09, you would tell the calculator to do a normal CDF from negative 99 to 2.09. Okay, here's how we actually calculate the z-score. If a normal distribution has a mean of mu and a standard deviation of sigma, then the z-score is x minus mu over sigma. Okay, what this means is you're going to take the number that you're interested in, subtract the mean, and divide by the standard deviation, and that gives you the z-score. It's one of those things that if you take a statistics course, you will use it so much it just becomes very easy to memorize, easy to get in there. I think it may be on your formula sheets, and we'll check for that. Now, what's the deal with the z-score? Well, the second box here says the area under a normal curve between x equals a and x equals b, those being two data points, is the same as the area under the standard normal curve between the z-score for A and the z-score for B. So it allows us to use the standard normal curve to calculate the area rather than trying to create a normal curve based on your data, which again, if you take a statistics course, you'll do that. You will learn to create a normal curve based on your mean and your standard deviation for your data, and then you'll learn also to convert it to a standard curve. We're not going that deep into this, we're just comparing it straight to the standard normal curve. Okay, here's some examples. So you're going to find the given z-scores, the z-scores for these given numbers rather. So pause the recording, give it a try, and resume to check your answer. Okay, remember the z-score is simply the x value minus the mean divided by the standard deviation. So 65 minus 60 is 5, divided by 5 is 1. And for part B, okay, you have 52.5 minus 60, which gives you negative 7.5. Divide that by 5 and you get negative 1.5. So the z-score is negative 1.5. This question, pause the recording, give it a go, and resume to check your answer. Okay, so we have the mean of 1200 and the standard deviation of 150. We want to find the area under the normal curve between 1200 and 1600. So we'll find the z-score for 1200. Well, the z-score for 1200 is 0 because when you create a standard normal curve, your mean becomes 0. Find the z-score for 1600, and we put it in the formula and get that that is 2.67. And now what you can do is on your calculator, do a normal CDF from 0 to 2.67, and you should get 0.4962 or 49.62%. Now find the probability that the salesperson drives between 1,000 and 1,500 miles per month. Pause the recording, give this a try, and resume to check your answer. Okay, so we need to find the z-scores. We already found the z-score for 1200, but now we need to do 1000. Putting it in the formula, we get negative 1.33. Putting 1500 through the formula, we get 2. So we want to do a z-score, we want to do a normal CDF from a z-score of negative 1.33 to a z-score of 2. Put that in your calculator and you should get 0.8855 or 88.55%. All right, next example. It says with the data from the 2009-2010 National Health Nutritional Examination Survey, we've seen this one before, we can use 186 as an estimate of the mean total cholesterol level for all Americans age 40 and 41, as an estimate of the standard deviation. So the mean is 186, the standard deviation is 41. Assuming total cholesterol levels to be normally distributed, that's important because you don't ever want to do a z-score and put it on a normal curve if it's not normally distributed, so they'll usually tell you that. What is the probability that an American chosen at random has a cholesterol level higher than 250? If 200 Americans are chosen at random, how many can we expect to have the total cholesterol higher than 250? All right, so you've got two tasks here. The first one is to find the probability that the cholesterol is 250 or greater. So you need to find the z-score and then go from that z-score to the end of the curve. We talked about how to do that a minute ago. And then you need to find how many out of 200 Americans would be expected to have that. Now you may have forgotten how to do this. We have done this before. Think expected value from chapter 9. Pause the recording, give this a try, and resume to check your answer. So we have our mu and our sigma, and using those with 250, we get a z-score for 250 of 1.56. And again, what you want to do is put that into your calculator. You want to do a normal CDF. You want to do 1.56 to 99. And when we do that, we get 0.0594. So 5.94%. And then what you do to find the probability of a randomly chosen person, that would be the probability of the randomly chosen American having a cholesterol higher than 250. Now, out of a group of 200, how do you figure out how many would probably have cholesterol higher than 250? Well, you multiply 200 by the probability. So 0.0594 times 200 gives us 11.88. So about 12. You can't have 0.88 of a person, so you would say about 12 can be expected to have a total cholesterol level higher than 250. Now the areas between each opposite standard deviation on the normal curve, and by that I mean the standard deviation of 1 and -1, of +2 and -2, etc. They have been calculated for the standardized normal curve, and they are summarized by what's called the 68, 95, 99.7 rule. And you see the curve here, and the numbers are slightly off. We say 68, 95, 99.7. They're actually a little bit more than that, a little bit different, but the 68, 95, 99.7 is just really easy to remember that way rather than getting into too many decimals here. But what the rule tells us is that 68% of the data is going to fall, or 68.2% really, is going to fall between the first and positive and negative standard deviation. So between -1 and 1 on the normal curve, on the standardized normal curve, 68% of your data is going to fall between there. So that's little more than half are going to be in that group. Now, if you go out one standard deviation, you go from -2 to +2, that's going to represent about 95% of your population. And so you expect most of the really normal scores, like if we're talking a test or growth charts or whatever, is going to be between 2. Now, 3 is getting a little bit further out there, but between positive and -3 on the curve, you're going to have about 99.7% of your data covered. So there's very, very little data that's going to go beyond 3 standard deviations away from the center. And if you are doing statistics and you get a point that goes beyond 3, it's considered a very unusual point. And a lot of times it's a reason for us to go back and look and make sure we didn't write the point down wrong, or there wasn't something weird going on that might have affected the data when you see something that's that far away from center. Okay, folks, last topic of the semester, box plots. A normal curve is useful because it allows you to read various characteristics of a data set quickly. It gives you a good picture of what's going on. A box plot is another means of presenting key characteristics in a graphical format. And it doesn't say this here, but a normal curve is really great. Well, it has to be used with symmetric data. When you don't have symmetric data, you can't use a normal curve. And a box plot can be very handy when your data is not symmetric. So it's just another good way of graphically representing your data in a way that allows people to really get a good picture of what's going on. To create a box plot, you have to arrange the data numerically first, and then you have to find the median. Okay, remember, the median is the physical center of that lineup of data. Now you're going to find 2 more halfway points. You're going to find the point that's between the median and the minimum value. So the very beginning to the median, find the halfway point there, and that's called the first quartile, or Q1. Then you're going to find the point that's between the median, exactly halfway between the median and the maximum value, and this is called the third quartile, or Q3. Now, if you're wondering what happened to Q2, well, that's what the median is. It's actually Q2, but we don't call it that. We call it the median. Now, the minimum data value, along with Q1, the median, Q3, and the maximum, make up what is known as the 5-number summary. So you have the start, the end, and these 3 points in between that kind of divide it up into quarters. These 5 numbers are used to construct a box plot, which we're going to be looking at in the next few examples. And you can also construct a box plot on your calculator. What you're going to do is you're going to put your data in list 1 as usual. Then you're going to select the second plot on the second row. It looks like this. You see the picture there. In a more comprehensive statistics course, you would actually use the one on the left of that, the first one on that row. It's actually a little more precise, but we're not getting that deeply into it. We're not taking the time to explain the differences. So we're just going to use this general box plot here. Make it simple. So let's try this example. Pause the recording, give it a try, and then resume to check your answer. All right, so this is doing the box plot by hand. You have to put all the data into order from low to high. By the way, you can actually make your calculator do that too. If you put the data in list 1, and then let's see, you want to go to stat edit, you've got sort A and you've got sort D. Sort A is ascending, so if you want to put your list in ascending order, you can use that in numerical order from lowest to highest, and sort D would be descending. So you can even get your calculator to arrange the data for you if you need to do that. Although if you're using your calculator to construct your box plot, you don't have to put the data in order. The calculator can sort that out. Anyway, if you're going to do it by hand, you've got to order the data as you see here. The minimum is 64.8. The maximum is 90.8. There's our first two numbers that we need. There's an even number of data points, so what we need to do is take the two numbers in the middle and average them. And so we get the median, 72.2 after averaging. And then to find Q1, basically you have to go to the fourth, 25% of the numbers. So we're going to have to you're going to have to take actually the second and the third. Now here they do it a little differently. I guess different statistics books will do this differently. Generally what I've seen is you do it the same way you do the median. Like here, the first quartile, well, that would be between 66.2 and 68.0, and you would average them. Here this says just to go for 68.0. I guess either way to do it is fine, whichever way is being done by the book you're learning. Let your calculator do it, and then you find Q3 also. So you've got your 3 points. Now if you use your calculator, it may be slightly off because of the way they're doing the Q1 and Q3. It shouldn't be hugely off, just a little bit possibly. And there we've got them. And so you've got the minimum, the quartiles, the median, and the maximum. Now how you do a box plot, and by the way, this is also known as a box and whisker plot. You create a number line, a horizontal axis, and you can see here we've got it numbered 65, 70, 75, 80, and so on. And then for the minimum and maximum, you're going to put a small vertical line where those points are. You're going to put a little longer vertical line for Q1, the median, and Q3. And you're going to create a rectangle out of Q1, the median, and Q3, as you see here. The median divides that, and then you're going to make lines from the ends of the rectangle out to the minimum and maximum. And you can see why it's sometimes called a box and whisker plot. Those two lines would be known as the whiskers. Okay, now try example 7. You're going to use the same data as in the last example, but this time you're going to create a box plot for Home Depot, and you're going to do it on the same graph. Let's pause the recording, give this a try, and resume to check your answer. And again, we go through the process of finding all the 5 data points that we need for our 5-number summary. And once we have those, we put them on the graph, on the same graph as the Home Depot. So Home Depot and Lowe's are there together. And this is a good way to be able to compare things. So you can compare how the two stores are doing with each other in revenue. You can also get an idea of the shape of the data. I can tell by how close the median is on Lowe's to the right that the data has a long tail to the left, which means it's skewed to the left. Home Depot, on the other hand, the median is a lot closer to the left end of the box, so it is actually skewed to the right. The tail is to the right. So you can see different things. You can compare medians. You can just get a lot of information by looking at two box plots on the same scale. You can graph two box plots on the same plane using your calculator. You just need to turn on two different plots at the same time. Since you'll have two different data lists, one would need to be list 1, the other would need to be list 2. You just need to make sure you've got all that fixed up in the plots when you turn them on. You can, when you've got a box plot on your graph, if you use the trace function, if you hit trace and then you use the right and left arrow key, what it will do is it will jump between the 5 numbers and the 5-number summary. So it'll give you the minimum, the maximum, and at the bottom of the screen it will tell you what those values are. And just a reminder, the one variable stats function will give you all 5 numbers you need to construct a box plot. So if you're going to do this in your calculator, just put the data in the list and then run one variable stats and you've got it. By the way, if you're going to put two lists in at the same time for two different sets of data, if you want to do the one variable stats on a list that is not list 1, like let's say you did the first one and you want to keep it, so you put your second set of data in list 2. Then when you choose one variable stats and you hit enter and you get the home screen, before you hit enter to calculate anything, you need to tell it that you're using list 2 or 3 or whatever. And how you'll do that is by hitting the second button. And then if you're using list 2, you'll hit number 2 and it should say L2. And then hit enter and you're fine. The calculator assumes if you don't put a different list name in there that you want it to use the data in list 1. So it's really important if you are doing different lists that you make sure your calculator understands which list you're interested in getting the graph and the data and the statistics for. Extra practice, so pause the recording in between problems and between slides. Resume the recording to check your answer. And do this until the end of the recording.